So volumes, as I'm showing here in this table, this is an illustration of volumes and rate of flow within 1 hour. For example, there is 1000 vehicles counted over 15 minutes intervals. This can be expressed as 1000 vehicles over 0.25 or times 4, and that would give me the volume, or the expected volume, which is the flow rate, is about 4000 vehicles. So if someone of you sent a technician from 5 to 5:15 to that intersection, and you would have 1000 vehicles for that 15 minutes, then what you would do, you would either divide it by 0.25 or multiply by 4, and this would give you an estimate of 4000 vehicles. If I send the technician now on the second quarter, so as he's gonna count 1100, and now I'm gonna be having what, for 4400 vehicles per hour as an estimate of the flow for the entire hour. And same thing goes all the way to 5:45 to 6 p.m., where now people will be going almost done and everyone is there in their homes, and that's why the volume now is getting much less. So if you were to send a technician at the last quarter of the hour, then the estimate of the flow rate would be 3600 vehicles. So as we said, again, the rate of flow of 4000 vehicles here for the first 15 minutes again would give you an indication that, again, for that 15 minutes only, is it gonna give you the worst case condition? No. The worst condition here, it looks like it was the third quarter of the hour from 5:30 to 5:45. The summation now, what's interesting is if you stay for the entire hour observing cars, you would see that the summation is 4200. It's not 3600 like the last quarter, neither like the very first quarter, which was 4000. So again, that shows you that if you have the capabilities and the chance and the resources to do a full hour, this would be the most accurate number to represent that intersection. So I think this slide here summarizes what we already talked about. So in summary, the full hourly volume and the sum of the 15 minutes were about 4200 vehicles per hour. The rate of flow for each 15 minutes interval is basically, it's the volume observed for that interval divided by 0.25 hours. Why? Because again, it's 0.25 is 1/4 of an hour, or we can, as I said, we multiply the rate or the flow in 15 minutes times 4, and that will give us an estimate of the flow rate for the entire hour. And as we could see, that the worst period of the time was somewhere between 5:30 and 5:45, where the rate of flow is about 4800 vehicles per hour. This is the flow rate. Again, it's not a volume. The volume, if you would stay for the entire hour, and that would give you the actual volume of 4200 vehicles per hour. Another look here at another table, the same intersection. Now table 5.4 in your textbook really here compares the demand and capacity for each of the 15 minutes. As we said, even at the peak hour, the intersection might be really good in 15, 20, 30 minutes, and then the rest of the 30 minutes might having issues. So let's take a look at this example, and now we're gonna be calculating the amount of the queue, the queue size at the end of each period. So the queue at the end of each period can really be computed as, first of all, the queue at the beginning of the period plus the arriving vehicles at that 15 minutes in particular minus the departing vehicle. So what does that mean? So this here shows you the arriving vehicles. So from 5 to 5:15, we've got 1000 vehicles arriving to the intersection, while the departing vehicle, as you could see, is pretty much constant. This is how much the intersection can handle. So this is here, no matter what arriving vehicles we have, the departing vehicles is always will be 1050 vehicles. So this is the capacity, if you will, of the intersection, and this is what we are experiencing in terms of arriving vehicles. So in the very first 15 minutes, there is 1000 vehicles arriving, while the intersection can handle 1050 vehicles. What does that mean? That means we're not gonna have any queue. All the cars arriving, they will be departing on time, no queue by any means. Now the second 15 minutes, from 5:15 to 5:30, again I have another 1100 vehicles, and the capacity is constant as we said. So the capacity is 1050. So the queue size at the end of this period is basically 0, which is how many vehicles were accumulated at the previous 15 minutes, plus the coming or arriving vehicles, and that's 1100, minus what the intersection can handle in that 15 minutes, which is 1050. And now we could see that at the end of the second 15 minutes, we're having 50 cars accumulating at the intersection. Now now going to the third quarter of the hour, which now this looks like the worst time of the peak hour, 5:30 to 5:45. Now we're having 1200 vehicles arriving, and the capacity is constant, which is 1050. So how are we gonna calculate the queue size now at the end of the third quarter? First of all, we have 50 vehicles accumulated from the previous 15 minutes. So that's 50. Plus the 1200, which is the arriving vehicles at that 15 minutes, minus the capacity of the intersection at that 15 minutes. So it's 50 plus 1200 minus 1050, and that's gonna tell us that by the end of the third quarter, by 5:45, we will be having 200 vehicles accumulating at the third quarter. Things now again is gonna start to improve by the fourth quarter of the hour, simply because now the arriving vehicles are much lower than the previous quarter. So now I'm having 900 vehicles arriving to the intersection. The capacity is constant, 1050. So how am I gonna calculate the queue size here? So it's gonna be the 200 that they were accumulated from the previous quarter, and then we're gonna add this to the 900 arriving vehicles at the last quarter of the hour, minus 1050, and now this is gonna tell us that there were 50 vehicles accumulated at the end of the peak hour. So out of all the calculations that we did here, we always like to come up with the peak hour factors. It's basically a relationship between the hourly volume and the maximum rate of flow within that hour. And again, the way to define it is the peak hour factor. As we could see here, the peak hour factor is simply the hourly volume, which is the entire volume if you would stay there for a full hour, over the maximum flow rate. So in the previous case it was about 1200, and that's how are we gonna use it in a second. So typically we measure volumes every 15 minutes, and that's why we can simplify this equation here into another form of the equation, which is peak hour factor is basically V, which is the hourly volume in 1 hour, over the maximum 15-minute volume within the hour, which is this one here, times 4. Why 4? Because I'm having 4 quarters, 4 15 minutes in an hour. If it happened to be that you are measuring the volume every 10 minutes, that means you're having 6 10-minute segments in the hour, then V over VM10 times 6 would calculate for you the peak hour factor. But again, 99% of the literature we would be using 15 minutes analysis period, and therefore if you use the previous tables 5.3 and 5.4, you will be able to calculate the value of the peak hour factor to be 4200 over 1200 times 4, and that would give us a peak hour factor equal to 0.875. Again, as a reminder, if the volume is constant for the four quarters, that means the peak hour factor is gonna be what? I'm gonna let you think about it in a second before I tell you the answer. So if I have the same amount of rate of flow every single 15 minutes, and then I multiply that by 4, is gonna give me the exact peak hour factor equal to 1. So what does that mean? As a traffic engineer, I would like to see the peak hour factor approaching 1, meaning that there is a uniform amount of flow going through the peak hour factor, and therefore the queue size would be very minimal. While if the peak hour factor will be approaching very low number, let's say 0.1 or 0.2 or 0.3, that really means that there is a 15 minutes within that peak hour factor that is really bad. Most of the traffic is gonna go through that 15 minutes only, and then the rest of the hour is pretty much empty. And this is where you as a traffic engineer need to step up and find the solution for that situation. So peak hour factor approaching 1, that's good. Peak hour factor approaching 0.1, 0.2, 0.3, again this is very alarming number, and we would need to fix that issue. Another macroscopic parameters that we tend to calculate as traffic engineers are the speed and the travel time. So we all know that speed is basically the rate of motion in distance per unit time, and the travel time is the time that we take to traverse or to move a defined section of a roadway. So that's the time taken again to move at any defined section on a roadway. So to simplify what we just said, the speed and travel can be inversely related in this equation here. So S is the speed, miles per hour or feet per second, equal the distance traversed, either miles or feet, over T, and that would be the distance, the time. So that would be the time to traverse distance, D, and that typically we deal with it as hours or as seconds. So as we learned from the previous class, that there are two types of speeds. The first speed here is the time mean speed, while the other type of speed is the space mean speed. So what is the time mean speed again? Time mean speed is basically it's the average speed of all vehicles passing a point on a highway over a specified time period. So we are really here interested in averaging all the vehicles at a certain time, rather than the space mean speed, which is basically an average speed of all the vehicles occupying a given section of the highway or over a specified time period. So if you take a look at this picture here, the time mean speed, basically there will be a person, an observer, be sitting right there and now measuring the speeds of the cars in lane A and lane B, and then taking the average of these two. So for example, this very first vehicle here on lane A, it travels this distance, which is 176, or it has, again, let's concentrate on now on the speed. It has a speed of 88 feet per second. That means it's gonna move from this point to this point in 2 seconds, while this vehicle here, or the vehicles on lane B, it's a bit more congested, as you could see, and therefore the speed of each vehicle is gonna be less. It happens to be, in this case, the speed of the vehicle at B is 44 feet per second. So getting the TMS, which is the time mean speed, you are really sitting here and you are just measuring the overall average between a car passing at A and a car passing at B. Therefore the time mean speed would be 88 plus 44 over 2, and that would be 66, and that's what we're gonna see in the next slide. While space mean speed is really, now we are interested in the overall speed of all the vehicles at certain section, at certain space, and that's why we say a space. It's not just at certain time, it's now at a certain space, and this is why here, if we are, the observer would be sitting somewhere here, he needs to, or he or she needs to be looking up at the intersection from an upper point to see how many cars and what's the speed of each individual car. So it happens to be here we're having 1, 2, and 3 vehicles, and we need to lump sum the 3 of them together and get the average. So it's gonna be 44 plus 44 plus 88 over 3, and that would be the space mean speed. So that's here what I summarized in a second. So a vehicle would pass the observer in lane A every 176 feet over 88, so it's every 2 seconds. Similarly, the vehicle would pass the observer in lane B every 2 seconds also, because it's congested, so it's gonna have a distance of 88 feet over 44, which is the speed, and that's also gonna take 2 seconds. Therefore, as long as, again, the traffic stream maintains as it is, so for every N vehicles traveling at 88 feet per second in lane A, the observer would also observe a vehicle traveling at 44 feet per second at lane B, and therefore the time mean speed would be simply 88 plus 44 over 2, and that's gonna give us a time mean speed equal to 66 feet per second. Now the speed and travel time from the perspective of the space mean speed. So to measure that, basically, as I said before, the observer has to be a bit elevated at an elevated location from which he could see the entire space, which is the 176 feet, and then basically again here, however, as long as the traffic stream remains stable and uniform, there will be about twice as many vehicles in lane B, as you could see in the figure, compared to lane A. So to get the space mean speed is gonna be simply 88, because it's just one car at lane A that's gonna pass by, while in lane B you will see 2 cars, every one of them has a 44 feet per second speed over 3, because you will be observing, again, if everything stays as it is, you would be observing 3 vehicles at that section of 176 feet, and therefore the space mean speed would be 58.7 feet per second. This is here again another example, illustrative computation of both TMS and SMS. So here we are having 6 vehicles, so vehicle number 1 all the way to vehicle number 6, and we are having a fixed section. So the section of interest, or the space of interest now, is going to be 1000 feet. So again, an observer would be sitting at an elevated place to see the entire length of the section, which is 1000 feet, and we would be also measuring the time travel, or the travel time. So every vehicle, for example, the very first vehicle, it traveled 1000 feet in 18 seconds, and therefore the individual speed for vehicle number 1 is 1000 over 18 seconds, and that would give us a speed of 55.6 feet per second. We're gonna go now to vehicle number 2. It's passing by the same exact distance in 20 seconds, so 1000 over 20, and that's gonna give us 50 feet per second. All the way to vehicle number 6 traveled the same 1000 feet in 20 seconds, and that's why the speed is 50 feet per second. So based on this now, how can we use those observations to calculate both the TMS and SMS? Here, as you could see, first of all, the average distance is the same because every single vehicle passed through the 1000 feet, so the average distance is 1000 feet, and the average travel time is 19.8. How did we get this? If you sum up all the travel times of the 6 vehicles over 6, it's gonna tell you that on average every vehicle needed 19.8 seconds to pass by that 1000 feet. When it comes to the speed, now we can lump sum again all the speeds from 55.6 all the way to 50, divide them by 6, and that's gonna give you the overall average speed, and this is 50.6. This is the time mean speed. Time mean speed is 50.6. Why again? Because as we said, we're not interested in distances here. I'm just interested in lump summing all the individual speeds, divide them by their number, and that would be it. This is time mean speed. While the space mean speed, I'm really now interested in the section, within that distance. So now I'm gonna say it's overall I have the average length, which is 1000 feet, over the average time, which is 19.8. So 1000 average distance over average time, and that's gonna give me a speed equal to 50.4 feet per second. Again here, typically both of them are close, and they will get closer and closer when the speed of each car is exactly the same as the previous vehicle or the one that's gonna come after it. For example, if the exact time, the travel time is always 18 seconds for all the 6 vehicles, then time mean speed is gonna be exactly similar to space mean speed. And again, each one of those will have sometimes its own usages, and I would encourage you to look them up and see what are the applications of each one of those. Now we are also continuing here in the macroscopic parameters. We'll be talking about density and occupation. So we talked about density before, and density is simply the number of vehicles occupying a given length of a highway or lane. Generally it's typically expressed as vehicles per mile or vehicles per mile per lane. So we tend to see and look at the density as a very difficult parameter to measure directly. Again, we typically try to compute it from speed and flow rate measurements, and it's very important measure of quality, so we understand its importance, but in the same time, again, it's very hard to measure, and therefore we try to correlate it to other easier parameters to measure in the field, and that would be the occupancy. So what is occupancy? So the occupancy, basically, we are now using a detector. As you could see here in this illustration, I would have a detector embedded beneath the surface of the pavement, and now I have a vehicle, and once the vehicle is gonna pass by the detector, again, some calculations will be done as I'm gonna talk about it here in a second, and I'll be able to estimate the density at that intersection. So occupancy is basically, it's a time. It's the proportion of a time that the detector will be occupied or covered by a vehicle in a defined time period. So the vehicle is gonna come, and now it's gonna hit the detector for a certain amount of time very quickly. Again, we're not talking about seconds, it's maybe even a portion of a second. So LV, this is the length of the vehicle. LD, this is the length of the magnetic loop detector. So if the occupancy over a given detector is O, which is again certain amount of time, let's say 0.1, 0.2 seconds, then the density may be computed as this following equation. So density is equal to 5280, and again, if you would guess, this is basically 1 mile in feet, times O, that's the time, over the length, which is LV plus LD, and that's how am I gonna get an estimate for D. Let's have here an example to understand that concept. So let's assume that detector is generally activated, and here, before we go to the example, I just want to mention that the detector is generally activated as the front bumper engage the front boundary of the detector. So once the vehicle again pass by the very first front bumper, it's gonna hit the detector. This is where the detector will get activated. So consider now a case in which detector records an occupancy of 0.2. and again 0.2 is 0.2 seconds, for a 15-minute analysis period. If the average length of the vehicle is at 28 feet and the detector is 3 feet long, what is the density? So it's gonna be 5280 times 0.2 over the 28, which is the length of the vehicle plus the length of the detector, and that's gonna give me an estimated density equal to 34.1 vehicles per mile per lane. Another now microscopic parameters. So now we're moving from macroscopic to microscopic. Microscopic parameters such as spacing and headways. So spacing is simply the distance between two successive vehicles in traffic lane. So to get a good estimate of the density based on the spacing is using this equation here. So the average spacing in a traffic lane can be directly related to the density. So if I tell you that dA, which is the average spacing between each two vehicles, is certain amount of feet, you can divide 5280, which is 1 mile, over the amount of average spacing, and that's gonna give me an indication of the density in feet mile per lane. While headway is basically the time interval between the two successive vehicles as they pass a point along that lane. So I can get an estimate of the rate of flow based on the headway. So as you see in this equation here, the rate of flow, which is vehicle per hour per lane, which is another definition for the density, can be estimated as 3600 seconds over the average headway in seconds, and that would give me an estimate for the rate of flow. So based now on the average headway, which is HA, and the average spacing, which is DA, the average speed at that intersection can be empirically computed based on both parameters, headway and spacing. So this is the empirical equations, which is based on observations, is equal to 0.68 times the spacing, or the average spacing, over the average headway, and that would give me the space, or the speed, I mean. So let's here have a problem, sample problem, to summarize what we talked about in terms of speed, density, and flow rate. So traffic in a congested multi-lane highway is observed to have an average spacing of 200 feet. So that's the average spacing. That means on average the distance between two successive vehicles is 200 feet, and average headway of 3.8 seconds. So again, now the time between two vehicles to hit that detector is 3.8 seconds. Now the question here is asking us to estimate the rate of flow, density, as well as the speed of the traffic in this lane. So the very first thing that we can get is the rate of flow. Rate of flow, as we said, it's 3600, which is a constant number of seconds per hour, over 3.8, and that's the average headway. So if I divide 3600 seconds over the average headway, this is gonna give me an estimate of the rate of flow equal to 947 vehicles per hour per lane. When it comes to the density now can be also defined as 5280 over 200, which is the average spacing. So if you divide 1 mile, which is 5280 feet, over 200 feet, that would give you an estimated density of 26.4 vehicles per mile per lane. And lastly, to get an estimate for the speed, we're going to use this empirical equation, which is 0.68 times 200, which is the average spacing, over 3.8, and that is the average headway, and this is going to give me the speed, or estimated speed, of 35.8 miles per hour. Some of you may ask, how about if I multiplied the density times s times the speed? Shouldn't this give me the rate of flow? And in fact, if you do it, it will be very close. If you use your calculator, for example, and you would put 35.8 times 26.4, it's gonna give you the exact answer is 945 vehicles per hour per lane, while here you're having 947. So there is the difference of 2 vehicles per hour per lane, and again that difference is due to the round off errors, nothing much. But the three equations here, they are really interrelated, and this is how you can double check your answers. So again, if you multiply D times S, it should give you a very good estimate of the flow rate. Now let's move on to the very famous three figures here, which are the relationship among the flow rate, speed, as well as density. So the very first figure here, we have flow versus density, and we have flow versus critical speed, and we have density versus speed as well. And I know we talked about this before, but here we will be talking about it in different perspectives. So first of all, we're having two types of lines here. We have this continuous line and we have a dashed line. Same thing when it comes to flow versus speed. And when it comes to density, here all the way to this point, which is the critical density, and after that we're having a continuous line, not a dashed line. So a continuous line versus a dashed line. One thing here that I want to mention, that the continuous line is we call a stable flow versus a dotted points or a dotted line, this is a forced flow. So in more details, let's talk about those things in bullet style. So as you could see from the previous graph, the flow rate of 0 vehicle per hour can occur at two different conditions. So the very first condition, and let's here try to draw this relationship. We were able to see that the flow, this is the flow rate, were 0 at two conditions here. Condition 1 versus condition 2. Condition 1, when there is no vehicles. Again, I can see a flow rate equal to 0 vehicles per hour when there is no vehicles on the highway. So density is basically going to be 0 vehicles per mile, and no vehicles can be observed passing that point. So under this condition, which is here, speed is typically, you can't even measure it, it's unmeasurable, and we refer to it as free flow speed. Free flow speed, that means again pretty much hardly no vehicles, and the speed is going to be equal to free flow speed. While the other condition, which is way different, this is again it's a flow equal to 0 vehicles per hour. This also occurs when there are so many vehicles on the road that all motion stops. Here this is where we call the jam density, where now the intersection or the highway is fully occupied by vehicles to an extent that no vehicle can move by any means. So that's here the jam density, and again the flow equal to 0 simply because all the vehicles are stopped. As I was saying, and I was pointing to the figure, also the dashed portion of the curve represent unstable or forced flow. What does this mean? It's really representing flow within a queue that formed behind the breakdown location. You don't want to have this. As a traffic engineer, you would always love to be on the other side, the stable flow. The solid line portion of the curve represent that stable flow, which means it's a moving traffic streams that can be maintained over a period of time. So except for capacity, flow and flow rate may exist under two conditions. Again, the capacity flow can be again under two conditions. I can have a good flow on two conditions, either relatively high speed at low density, which is going to be on the stable portion of the flow rate, or I can have it a good capacity and a good flow rate at relatively low speed at high density. And again, this happens at the unstable portion of the flow relationship. So which one again you want to be at? Again, as a traffic engineer, you would always prefer to keep all the facilities operating on the stable side of the curve. So to summarize this again, we're having this relationship here, and again we're having a stable line, and then this is a dotted line. So I can have the flow, this is the flow, and if I pick certain line, this amount of flow here is the same as here. But definitely you want, as a traffic engineer, to be at this case, which is a stable line, which is relatively high speed and low density. Lots of again, the density is not that much, but the speed is high, and the flow here is really good, compared to exact same amount of flow, but this time is associated with what? Low speed and high density, which is unstable condition that happens often. And as a traffic engineer, you would always like to keep your facilities at this portion, at the stable portion. With that, again, I think we finish chapter 5, and thank you so much.